All right, so why don't we go ahead and get started. So welcome back, everybody, to EE290C. So before we sort of dive into the core material and all that, I just wanted to check sort of one thing. Obviously, homework is due today, so if you're here in person, just drop it off over here in the front, or if you didn't already, you can put it in the box near my office. Other than that, how many of you guys have already sort of figured out who your project partner is going to be? Okay, so I know there's at least a couple of people still looking based on sort of the hands and just people who have mentioned to me. So if you haven't figured out a partner already and you're still sort of looking for one, then please send me an email so I can kind of pair you guys up. And actually, why don't we even do this? Why don't you guys already, if you know your group, then just send me a quick email with like who's in your group so that I can see like, if there's one odd person or something like that, then I can also sort of try and tack people on if necessary. Okay, so that's actually mostly it in terms of the logistics kind of stuff, other than obviously next week is ISC, so no lectures. We'll pick back up the following week. And then, again, just pay attention on the website for posting the homework, because there will indeed be another homework that I'll put up in the next kind of few days or so. So before we kind of dive back into stuff for today, which, as I mentioned, is going to be getting really back into the sort of circuit design part of things, is there any questions on anything that we've talked about so far? Or? Can we maybe actually close the door back there, or just ask them if they want to shift over a little bit? Thank you. So, any questions? Or? Yeah.
So a lot of time we talk about like edge sampling versus like the sample bit sampling, but do people actually bother about equalizing the edge sample?
Okay, so great question. So most of the links that I've seen, let's say the commercial links, don't really do much to equalize the edge sample explicitly. So we'll talk about it more later on when we get into sort of CDR design, but usually they'll just basically ensure that they've averaged things enough sufficiently afterwards that any sort of, let's say, zero mean types of errors will just get averaged out. And then the only residual problem you have is that you might not be locked onto the right nominal position. So how big of a problem that is depends on who you really talk to, but for at least up to about 10 gigabits per second or so, that's generally not too big of an issue. So most of the designs that I've seen, like I said, generally have not been doing too much of the sort of fractional equalization kind of stuff. Maybe that will change when we get to the higher data rates, but so far, that seems to be how things are going. Other questions? Or? Okay, so if there's no other questions, then let's actually go ahead and dive back into things. And so for today, and maybe we'll finish sort of things up on next time, what I really want to mostly talk about is actually equalization in terms of the circuit design side of things. So we talked about, continuous time linear equalizers, we talked about FIR equalizers, we talked about DFE. Now is where we'll really see how we're actually going to build these things, okay? So to start out with, I just wanted to kind of go over quickly the kind of CTLE. And I will do this fairly quickly because I'm going to assume, again, that you've seen a lot of this from 240. But I'll kind of maybe give you a little bit of a reminder on things and maybe sort of cast things into a more direct form so that there's maybe less questions about how you'd go about actually really designing one of these things. So the first thing that I'll just mention is in terms of continuous time linear equalizer, you could obviously do that on either the transmitter or the receiver. But generally speaking, it's a lot, let's say, easier or more, let's say, more efficient to do it on the receiver. Simply because on the receive side, you're dealing with kind of a smaller signal due to the loss of the channel anyways, A. But B, more importantly, you're generally dealing with much higher impedances than you are on the transmitter. Okay, so on the transmitter, you've got to drive that 25 ohm equivalent load that you get from a double terminated link. Right, so if you want to do anything in sort of voltage, it costs you that much more current than rather at the receiver, where you're really just driving the parasitic capacitance of the following stages. Right, and that parasitic cap is generally pretty small, which means that even at, let's say, 5, 10, 20 gigahertz, the impedance you see there is still much higher than the impedance that you'd get from the channel itself. Okay? So the other thing that I just sort of want to kind of generally remind everybody about is that when we usually talk about these sort of receive, or actually in general these linear equalizers, if this is kind of what my channel looks like, and just for simplicity, let's assume that it's kind of a first order channel. So let's say it looks something like this. Okay, so just as a reminder, obviously if I have a channel that looks like this, then what I usually want to do at the receive side is basically just a high-pass filter. Right, so I basically would want to do something that kind of looks like this. Now, if I could keep on going forever here, that would be great, but obviously no real circuit can do that, so you have to put some finite bandwidth in. So generally, of course, you'll put the 0 at wherever the channel pole actually is. And again, I'm assuming a very simple channel here, but the concept is basically the same even for more complicated channels. And then, of course, in terms of the bandwidth you want to achieve, that's usually just set by your signaling rate. Okay? Now, you should keep in mind here that, again, because this is a real circuit, right, anytime you have a 0, that generally also means you have to have a pole there. So in order to sort of get the shape that I'm showing you, you will generally have actually 2 poles at that particular point. Okay? So in other words, whatever your bandwidth is, you're going to want to try and place both of your poles at that bandwidth. Okay? Because you can kind of think about it, if the 2 poles are sort of separated from each other, then actually you're just effectively not getting as much signal swing as you could have gotten. Okay? So again, just as sort of a reminder, typically you're going to want to place those things at approximately 2/3 of kind of the bit rate. Okay? Where bit rate is just 1 over t bit. And if you're interested in exactly where that comes from, there's some math you can do to kind of deconvolve, or rather find that particular value. But ballpark, just take that as being a reasonable number, and turns out that actually holds pretty true over a pretty wide range of situations you might be interested in. Okay? Does this make sense to everybody? Or? Yeah.
But it should be FBW, right? Is 2/3 of...
Oh, I'm sorry. That's right. FBW. There we go. Thank you. Okay. Good catch. So yeah, indeed, that's typically where you will put the bandwidth. Okay? Now, one other thing I should just mention here is that when you actually build this thing, and we'll see one particular example in a second, when you actually build this thing, the way you typically will actually build it is what you would actually have is something that nominally would have looked like this. But what you're basically going to do is just throw away some of its DC gain. Okay? And the reason for that is that in general, if you could have just gotten higher gain in the first place, you would have gotten it. Right? So in other words, if I could have gotten this much gain at that frequency, then why the heck couldn't I have gotten it at DC? Right? So in reality, when you're usually building these equalizers, what you're actually doing is just taking some of the gain you would have had and throwing it away. Okay? And of course, you're doing that intentionally, because if you didn't throw away, you would get bit errors. Okay? But you should always keep that in mind from a sort of power consumption standpoint. Now, the only caveat is that, if I could have had maybe some inductors somewhere, I could do some weird peaking or something like that. But generally speaking, especially in these sort of high-speed links kinds of things where, let's say my linear equalizer is just driving a comparator, and, and this thing maybe only has 10 to 20 femtofarads of capacitive load. If you sort of think about how big of an inductor you'd need to actually get this kind of behavior, it's ginormous. Okay, it's just going to be a huge inductor, and it's not really going to be very practical for you to actually use it. This obviously depends on exactly which frequencies you're talking about, and how big your comparator ends up being and things like that. But generally speaking, this is basically where you land from a design standpoint. Okay? Does this make sense to people? Or? Okay, so let's just actually sort of take a quick look at how you build these things. And again, this should mostly be a reminder, because I know we talked about this quite a bit in 240. But the most sort of common thing that people will do, at least conceptually, is the source-degenerated continuous time linear equalizer. Okay, so just as a reminder, this thing typically looks something like the following. So you just take a diff pair, and then rather than sort of directly tying it to a tail node, what you instead will do is put some RC degeneration network in that tail there. Right? So you have some RS, some CS, some load resistance, and of course some load capacitance that you'll be driving. Okay? Now, and of course this is, let's say, Vn plus and Vn minus. Okay? So usually when you sort of first look at this thing, your instinct, especially as a circuit designer, is just to go and say, well, okay, I'm going to go and just choose some R's and C's and things like that. But at this point is where you should sort of say, well, wait a minute. I know what I'm actually trying to do. Right? I'm trying to build a linear equalizer for a particular channel that I'm dealing with. Right? So if you sort of think about it, you sort of think one level up from the system standpoint. If I was just a communication guy, I really don't give a crap what the resistance values and the capacitance values are, right? All I really care about is what is the kind of transfer function that this equalizer is implementing, okay? So what I want to just walk through really quickly is a way to figure out how you actually choose these component values based on what's the actual equalizer you're trying to build in the first place, okay? So again, sort of at the system level, you really only care about the following things. So the first thing you really care about is just where is the 0, right? Which, of course, just, if you've done things right, should be set at wherever the channel pole is in the first place, right? The second thing you, of course, will care about is just what's the bandwidth, which, again, you should just be really set by the data rate, right? And then finally, the only other thing you really care about is kind of how much gain is this thing giving you. Right, so let's just call that something like A peak. And you'll understand why I called this A peak in 1 second. Okay, so this is something like the peak gain, or really, let's say more like an effective gain. Okay, but that's just kind of saying, you know, it's an amplifier, so this thing potentially can give me some gain onto the signal. It could also be giving me loss, but you know, let's just assume we're going to specify that at the system level. Okay? Okay, so my claim is that just by giving you these 3 things, all of the component values, well, okay, those 3 things plus, you know, just what the load capacitance is, I can tell you immediately what all the component values should actually be. Okay? So let's just go ahead and sort of figure out what that, you know, how we were going to go about doing that. Okay, so if I tell you what the peak gain value I want to be is, from a circuit standpoint, what do you think is going to set sort of the quote-unquote peak gain in this structure? Yeah, it's just GMRL, right? Because if the degeneration, you know, just becomes a short, then I just get a GM, and I drive that GM into an RL, right? So as usual, my peak gain is just GMRL, right? Okay, well, what's my bandwidth set by?
RLC.
Yeah, it's just 1 over RLCL, right? Nothing magic here. And yes, indeed, there is another pole. I'll take care of that pole in 1 second. Okay? Because remember, I'm going to make that pole equal to this pole. But just like a normal, you know, simple amplifier, this is just 1 over RLCL, right? Okay, so now hopefully this is, again, you know, really just a reminder. So if I was to combine these 2 things, so hopefully how I choose the RL is obvious, right? So that's just 1 over the bandwidth times the load cap. What does the GM end up being? And again, this should be the absolutely standard result, you know, that you remember kind of off the back of your head.
One plus GMRL.
Oh, you could do it that. Well, I want it in terms of the bandwidth and the capacitance.
Okay.
Just based on, you know, what I've written here.
In bandwidth times L.
Yeah, remember, GM over C is just gain bandwidth, right? So GM is just going to, of course, be peak gain times capacitance times your channel times your bandwidth, right? And again, that's literally just saying GM over C is gain bandwidth. Okay, so I just move the C over to the other side. Okay, let me actually just rewrite it to maybe even make that more clear. The gain times the bandwidth is just the gain bandwidth, then times the load capacitance. Okay? Okay, so that's actually pretty easy. So now actually kind of all I really have left to do is figure out the source degeneration network, right? Because if you told me the V star, you could go and figure out what the drain current is, what the size of the devices are, and so on and so forth, right? So now all we really have to do is figure out the source resistance and the source capacitance, okay? So it turns out to do that, we just have to sort of keep in mind one thing, which is, remember we said that we would like to place the 0 at this channel pole, and we would like to place the bandwidth, which is going to be the pole associated with that source network, also at the same point as it was for the output network, right? The other thing to keep in mind is that for all intents and purposes, because this is just a first order response, the ratio of this gain to basically that gain is just set by the ratio of the poles, right? Or rather, the ratio of the pole to the 0, right? Because, again, it's just 20 dB per decade, which means linear increase in frequency gives you linear increase in gain, okay? So what that basically tells you is something like the following. If I'm interested in what's the peak gain divided by the DC gain, then as we just said, that should be set by the bandwidth divided by the location of the 0, okay? So now here's the question. What's the ratio between the peak gain and the DC gain in this particular structure? Okay, it's actually 1 plus GMRS. And to be more precise in this particular case, it's 1 plus GMRS over 2 because it's a differential thing. Okay, but it's exactly just that. It's 1 plus GMRS over 2. Okay? So now, if you want to know what your RS should be, well, guess what? It's easy. It's just the bandwidth divided by the 0, which, by the way, a lot of people like to talk about sort of, how much peaking you're doing. That's kind of telling you how much peaking you're doing. Minus 1 times 2 over GM. Okay? So now once I've done that, CS is also kind of trivial. So how do I figure out CS? What's that set by?
0.
Yeah, right, exactly. So I know where the 0 is. That's just at 1 over RS CS, right? So if I want to figure out CS, that's of course just 1 over RS times the 0. Okay, which if you just, take that value for RS and plug things back in, that just turns out to be GM divided by 2 times the bandwidth minus the 0. Okay? And I just skipped some of the steps for the math. Internally there used to be a W bandwidth over omega 0. There was an omega 0 outside of it. I just pushed it back in and sort of simplified it this way. Okay? So again, I mention this because if you think about you going and designing your link, what you usually get is where's the 0 and where's the bandwidth, right? Because you know your data rate, you know what the channel looks like. And then, okay, this A peak is kind of a parameter you can play around with, but you can pretty easily sort of get an idea of what you'd like to do there, right? And once you've done that, all of the values of the components are basically specified. Okay? Does this make sense to people, or?
So we can throw this in the bag?
Yes, that's right. That's exactly what you can do. You can put this into just some code that, you say this is what you want. It spits out an equalizer design for you. Okay, and actually, I'm only slightly joking because we've got things that almost basically do this already. Okay, it's really not that bad. And I'll tell you some of the, let's say, practical things to watch out for because, it is indeed a circuit, so there's always more fun to worry about. The first thing to worry about is just that basically, unfortunately, as much as I like to deal with infinite RO transistors, they don't really have infinite RO. They usually have pretty crappy RO. And in particular with this design, what that tends to do is sort of couple the dynamics that happen down here to the dynamics that happen out here. And then indeed, these equations kind of get a little bit messed up. Okay, well, good news is there's a very simple way to fix that particular problem. So what do you guys think you would do to fix that particular problem?
Cascode.
Yeah, exactly, Cascode, right? So you just say, okay, forget it. I don't want to deal with RO. I don't want to deal with, getting those things coupled together. Let me just Cascode my input pair. Oops. And then if you do that, even in a really crappy technology with only a GMRO of like 4 or 5, trust me, you can get this to work very nicely. It's not perfect, but to within a few percent error, it'll work just fine. Okay? So indeed, that's one thing you will typically have to worry about. There's another one which is actually slightly more subtle, but which is also definitely a practical issue, which is just that, even though I've drawn kind of a current source over here, that's obviously a real transistor, right? That real transistor has some output impedance associated with it. Okay? So from the standpoint of actually your ability to implement this, anybody know sort of how that might impact you? What's going to happen if you actually have some RO over here?
The peak gain will be reduced.
Almost. You said the peak gain will be reduced.
The output common mode will shift.
Okay, I don't actually care too much about that.
You shift your zero frequency, right? Because right now the RC is...
Okay, so you said you're going to shift your zero frequency. That's absolutely right. Now, this will maybe give you a hint as to what the real problem will end up being. You're right, it'll shift the zero frequency if I don't take into account, but let's say I take it into account. What's eventually going to happen? And by the way, if I took it into account, that would say that this RS would have to be, larger than nominally you would like it to be. And by the way, what happens, just pay attention to sort of what happens to this RS as you make the bandwidth larger and larger. What happens to the RS?
It's bigger.
Yeah, it gets bigger. So what happens if I want...
Up to a certain bandwidth.
Ah, there we go.
Break doesn't work.
Right, exactly. So what's really going to happen is that because of this RO, at some point, there's going to be some minimum conductance at that node. And if you wanted to peak it more than that amount, tough luck, ain't going to happen. Okay? So as an example, if you wanted to peak it by, let's say, I don't know, 20 dB or 30 dB, or let's be more aggressive, let's 50 dB, right? Unless this RO is 50 dB higher than kind of the GM that's sitting at that node, forget it, ain't going to happen, right? So what that basically says is, indeed, this kind of introduces a maximum peaking. Okay? Now, again, the good news is there's actually something you can do to fix this one too. What do?
Cascode.
Yeah, you cascode this thing too, right? So I'll just draw one sort of side of it, and I'll make my life easy. So indeed, if you run into that particular problem, that means that now you're going to have to make sure you sort of cascode that current source in some way or another, right? Okay, so now the quote-unquote bad news is that sometimes you actually have to do both of these things, right? Because sometimes you want high peaking, and you really want to make sure that you can design this thing very easily without worrying about the interaction between the two, right? So now you end up with something that kind of looks like, and I'll just draw maybe one side, but actually it's not so bad. Right, so you'd end up with something that kind of looks like this. Right, so now you've got 4 transistors in the stack plus the resistor on the top. Okay, a little bit painful, but good news is if you give me about a 1.2 volt supply or so, you can still probably actually fit this in reasonably well. Okay, if I had to do like 50 dB of peaking or something, that's probably not going to work, but most likely with 50 dB of peaking, your whole link's not going to work anyways, so you'd probably have to find another solution. Okay? So kind of the bottom line is that, this is actually, despite it's got some practical design issues, this is actually a pretty efficient way of building things. So you can actually do quite a bit of peaking at very high frequencies, and as long as your load cap isn't too big, you can actually spend only sort of, milliamp or less, maybe a couple milliamps at most for really high speeds in this particular equalizer block here. Okay? So indeed, this thing is actually quite popular these days because it's just a really efficient way of getting quite a bit of equalization. Okay? Make sense to everybody? Or? Okay. So, there was one other sort of issue which I've highlighted here, which I'll probably skip over for right now, just because we're going to be talking a whole lot more about it later on. But remember that anytime you build sort of a very high-speed amplifier, and I'll just draw kind of, the very simple picture, right? Everything that I sort of talked about so far was just assuming that I lumped all of the load cap as being some fixed magic number. But don't forget, you're always going to have some amount of cap just from your own diffusion parasitics. Okay? So in particular, if you're talking about a very high-speed design, it's going to turn out that sort of self-loading effect can actually have a pretty substantial impact on what's going on. Okay, so that's certainly something you have to keep in mind in this design as well. So as an example, if you wanted to go and take these equations, again, you'd have to muck with this GM a little bit based upon that. But I think we'll get to today, we'll actually derive exactly what the impact of that will be, just in a different context where it'll actually turn out to be even more important. Okay? Okay, so that's actually basically all I wanted to say about the CTLE, because again, I'm assuming you guys have sort of played around with this thing, but if anybody has more questions and stuff, please feel free to come and bug me. So for now, what I'd like to do is actually move on to talk more about the transmit side of things. Or rather, excuse me, to actually talk about FIR, sort of how you'd build an FIR filter, meaning to use that as an equalizer. So as I kind of, I guess, already hinted at, you will typically build these FIR equalizers on the transmit side. Okay, and as we'll talk about in more detail today, the reason for that is that, on the transmit side, you've got the digital data. So doing delays is really easy. It's just flip-flops. Okay? And as we'll see later, flip-flops are a lot easier than sort of analog delays. Okay? So if we look at sort of a typical mixed-signal implementation of one of these FIR filters, turns out there's a pretty sort of nice structure you get into. What you basically just say is, okay, well, if this was my main original transmitter, which let's just say was basically a diff pair, right? Then essentially if I want to build a filter, an FIR filter, all I really have to do is, let's say as an example, take the main data through some amount of current steering over here, delay it by 1, which again, this Z inverse is just a flip-flop. Then here I can control sort of the sign of it by just using an XOR. So this would decide whether or not I'm doing an addition or subtraction, right? And then again, just feeding that to another current steering pair over here, right? And then basically, and of course, I can continue doing this. So the idea is that essentially what I'm doing is that each one of these little analog, current switch kind of things is just acting as in the multiply, right? And then the addition is just happening out over here in the current domain, right? So just by summing all those currents together and feeding them into a single resistance, that's how I do the addition, okay? Does this make sense to everybody, or? Okay, so just a couple sort of points to point out to make sure that it's sort of clear, okay? So again, as I mentioned, this XOR here, that's just allowing you to flip between an add and a subtract, okay? So I've kind of drawn everything here on the left as being single-ended, just to make my life easy in terms of the drawing, but you should keep in mind this is usually done differentially, particularly to make that add and subtract easy, okay? The other thing is that basically the way you control those tap weights is just by tweaking that current source underneath there, right? And usually the way you'll do that is with some current mode kind of DAC sort of thing. Meaning you can digitally control the value of that current, and then by changing that, you will change the value of the tap coefficient, okay? The other thing to mention is just that, even though I've drawn this as kind of a diff pair here, I'm really just trying to steer the current to one side or the other, okay? So you will typically drive these pretty quote-unquote hard, because you're really just trying to either grab that current on that side or grab it on the other side. Having said that, you will usually keep them in SAT or maybe in subthreshold or whatever, just so that you're not so worried about the parasitics on that tail node there, okay? Doesn't have to be that way, but typically that's how it's done. Does this make sense to everybody, or? Okay, so now let's look at sort of, what this really means, okay? So kind of the most direct way to really build this looks sort of like I've shown on the right over here. So if this was my original sort of transmitter with no filter whatsoever, if I wanted to go and, let's say, build a 3-tap FIR filter, and in this particular case, I've used 2 post cursors, okay? So what you can see is that the way I've done this is basically, if I used to have, some transmitter that had sort of a maximum current to get a certain swing, then now to build kind of a very flexible equalizer, I'm just going to have each one of these be able to do anywhere between 0 and the maximum current, okay? So I could have this one do 0 max, I could have this one do 0 to max, I could have this one do 0 to max, okay? And by the way, the reason, of course, you have to do this is that, generally speaking, you're not building a transceiver just for one particular channel, but you have to operate over a bunch of different channels, right? So that means that you have to be able to program what the coefficients will really be so that you can tailor it to the particular channel you're interested in, okay? It may, of course, not even just depend on the channel. You could have some temperature drift or some other weird thing going on, right? So you pretty much always need to be able to program these coefficients, okay? So this is indeed kind of a really flexible way of doing things, because if you sort of think about what are the kind of possible equalizers you can build, right? So if this is, let's say, the absolute value of my coefficient, and this is kind of the relative time, or I should say maybe the sample time, right? What I can basically do is I can build something anywhere between, those values on that tap, where this is some maximum normalized value, right? I can do anything between that point and that point on the next tap. And I can also do anything between that point on the next tap, okay? So very flexible, that's nice, but no free lunch, okay? So the big sort of penalty that I'm paying here is that, notice, if I used to have a certain parasitic capacitance from this transmitter before, now by making the 3 taps like this, I've actually got 3 times as much parasitics. Right? Because if you think about it, each one of those switches has to be able to handle the worst case maximum current, which means that it's also going to have the exact same parasitic capacitance as that original transmitter did. Okay? So you can imagine, especially if I was going to do like a big equalizer with, 10 taps, 20 taps, something like that, very quickly you're going to build up a lot of parasitics here. Okay? And you should remember, in particular on the transmitter, it is actually a lot of cap, because remember, you're driving that, 50 ohms on your side plus 50 ohms in parallel on the other side, so, every one of those things actually has to do quite a bit of work, right? Yeah. Okay, it's a great question. So it depends on sort of which transmitters you look at. If you look at, let's say, the more traditional transmitters where people were trying to do like a volt or 2 volts differential peak to peak, you actually get a pretty reasonable amount of cap from the devices themselves. If not even really just from the devices, but even just from the fact of physically they're a certain size, and that causes you to have certain wires, and you partition things and things like that. If you do, let's say, a really good quote-unquote transmitter design where you have pretty low swings, then now you're probably largely dominated by the ESD and not so much by the device itself. So that is actually absolutely a fair point where, if you look at more modern designs, probably the parasitic cap on this output is not too big of a deal. But, we'll actually talk a whole lot more about this when we get into the receive DFE side of things. Okay? It's a great question, though. Yeah?
So can't you put a common buffer for all of them?
When you say common buffer, what do you mean?
I mean, like, have one cascode for, like, all those.
Okay. So it does turn out that if you put a cascode sort of on top of this whole thing, that does actually turn out to have some benefits. I'll maybe defer the exact reason why that has some benefits a little bit later on, because what I'd like to do is actually point out a little bit as to sort of where, why this is actually somewhat inefficient, even from a, let's say, communications standpoint. Because to really see what the benefit is, then we have to really understand that too. Okay, but to zero order, even if I put, let's say, okay, this is going to be tough to draw, but let's get rid of this and just, put a cascode there and put the term on the top, and then take the output from over there, right? If you think about it, if this cascode also has to handle at most 3 IMAX, then I haven't really done anything in terms of the parasitic loading on the output, right? So we're going to come back to why this cascode would actually help in 1 second, okay? Yeah?
So once you have multiple taps, then you have to rescale everything, right?
There we go. So that's absolutely correct, right? So
you
once I have multiple taps like this, you're absolutely correct that I'm never actually going to use IMAX on all of them, right? Because basically I would cause something to fall out of SAT, or or something would clip, or something like that, right? So that is actually very much related to why this is kind of an inefficient way of doing things. Okay, so that's actually a great sort of introduction into this next thing that I want to talk about. Okay, so the real reason why this is kind of inefficient is just coming from the fact that you don't really know what the channel is going to be ahead of time. Okay, so in other words, if I look at that kind of my pulse response, and I'm going to look at it just in absolute magnitudes instead of including the signs, because it's just going to make my life easier in terms of doing the drawing. Right, if you think about it, I could have, let's say, one channel that looks something like this, just as an example. And let's call that, let's say, channel 1. I could have another channel that, let's say the cursor just, I'll normalize it to be the same thing, but, let's say I maybe would have something like, I don't know, like this, okay? And obviously you could keep on doing this for all of the channels you could potentially ever run into, right? Okay, so if I was going to sort of build an equalizer for this thing, just exactly the same way as I showed in the previous picture, how would you sort of have to build that equalizer? In other words, what would be kind of like, and obviously I don't need numbers, but just conceptually, what would be like the worst case magnitude on, or rather, what would be the magnitude on each tap that you would have to possibly handle?
Max of any channel?
Yeah, the max of any channel, right? So you'd basically have to do this for the cursor. You have to do that for that first post cursor. This one for the next one, this one for the next one, this one, and so on and so forth, right? So in other words, you should remember that sort of the magnitude of the tap is proportional to that current that you're handling, right? And at the same time, your self-loading, and let me write that as, let's say, a C-self, is also proportional to that current, right? So like we just said, that parasitic capacitance is really now proportional to the sum of the max of those coefficients. And when I say the max, I mean the max over all possible channels you want to handle, right? Yeah?
So is this the channel response or the equalizer response?
Okay, so to be fair, this is really the equalizer that you'd like to build. But you can kind of imagine if the channel has a larger ISI coefficient, then your equalizer would also have a larger ISI coefficient. But you're absolutely right. This is really sort of the coefficients of the equalizer you want to use to deal with a particular channel. Okay, so when I say, I guess, max of, okay, maybe I should have called it W instead of H, but hopefully you get the idea. Does this make sense to people, or? Okay, so kind of the point which should hopefully be obvious now is that, as we said earlier, the signal swing is fixed, right? So in other words, we're always going to be rescaling the coefficients. Right? So what that really means is that if I actually look at any given one channel, if I actually looked at what was the sum of the magnitudes of my current coefficients, right? That would be just equal to some, let's say, peak value, and actually, whatever that peak swing that I want to get, right? Which now obviously would be a lot less than the sum of the maximum of the possible coefficients over all channels, right? In other words, if I said that, let's just normalize everything. Let's say that if my normalized swing is 1, right? And I tell you that, okay, the worst case on this channel is, let's say, 0.5, and this one is also 0.5, and let's say this one is 0.25, and this one is, I don't know, 0.1, and so on and so forth, right? Obviously, if I add all of these things up, I'm going to get something like 1.35, right? But I know that in the real thing, I'm never going to transmit more than, well, actually, excuse me, if I actually make this 1, I'd actually have a total of 2.35, right? But I know that in the real thing, I'm never going to transmit more than 1, right? Because I'm always going to rescale things to keep that same maximum magnitude, okay? So the real sort of fundamental reason why this is kind of bad is, again, that basically because you don't know what the channel is, now you're really paying more parasitics just because of that unknown sort of factor that you have to handle in the analog domain, okay? Does this make sense to people, or? Okay. So, given that that's the case, now here's the question for you guys. Can you build another transmitter that does not have this problem? And in particular, I'm going to remove power as a constraint for 1 second. And you'll see why I said that. And, Chintan doesn't get it to answer because he knows the answer already. But, what else could you do? How else could you build this transmitter so that it has as flexible of an equalizer as you'd like? So you can cover all of these worst case conditions, but you actually have no additional parasitic capacitance.
Can you play with time installed?
Play with time. What do you mean?
I mean, all the tabs fits the same current, but the time the time window you fit this current is changing.
Oh, so I'm not sure if this is what you meant, or maybe I just didn't understand it. But I think I'll show you something that's kind of like what you're saying in 1 second. But there's, let's say, an even more quote-unquote extreme solution that we can come up with that, is maybe, let's say, more obvious as to how it really would get rid of this overhead in terms of parasitic capacitance. So what else can you do?
Just build like a DAC.
Yeah, there we go. You just build a DAC, right? So if I just build a DAC, then I can just build that DAC, and here I'm going to draw it as sort of a current mode DAC, right? I just build that DAC where I have, some number of digital bits coming into this thing, right? And since I know what the peak swing is going to be, I just build it so that I put whatever transistor size I need to get that peak swing, and I just partition it into smaller units to act like a DAC, right? So as an example, of course, you could just do some standard current steering kind of thing, right? Where let's say this is the digital bit 0 bar. This is, let's say, digital 1 bar, right? And this would be essentially something like your peak current divided by 2 to the n bits minus 1. This would be your peak current times 2 over 2 to the n bits minus 1, and so on and so forth, right? So in other words, if you were to build this thing, you would just make it so that the sum of the currents in all of the DACs was just equal to whatever the peak current you actually wanted was, right? Okay, so what do I need to put in front of this DAC to actually do the equalizer now? Because the DAC by itself, it's just a DAC. So how do I figure out what I'm actually transmitting?
FIR filter?
Yeah, an FIR filter is, what kind of FIR filter is it?
Digital.
Yeah, it's a digital FIR filter, right? So I just build a digital FIR filter over here and use it to drive that DAC, right? So indeed, this particular solution gives you the minimum parasitic capacitance you can get, right? Because you've just put however much transmit sort of stuff you need to actually drive that final output, okay? So indeed, this works, you know, just perfectly fine. Okay. So now why? Well, okay, there are some people that are talking about doing these things and have actually played with these things in the past. Why does this usually not happen? Or why do most modern links not do this? Yeah.
That FIR is probably kind of a pain.
Okay, well, in pain in what sense?
Well, it has to be really fast, and it's a bunch of adders. And
Ah, there we go. Okay, so this is really fast and has to have a bunch of adders in it. Okay, and actually multipliers and all kinds of other fun stuff like that. Now, don't get me wrong, you know, you look inside your cell phone or something like that, there's a bazillion of these things in there, right? But this thing has to run at 10 gigasamples per second, 20 gigasamples per second, something like that. Right? It has to have some reasonable resolution at the output. So the typical problem you run into is that this burns a lot more power than sort of something that's an analog approach, or in fact something that's, let's say, maybe a little bit more clever, which I'll show you in 1 second. Okay? And by the way, just in case you don't believe me, because this is, you know, a discussion that I have many, many times with lots of different people about why the power of this is kind of tricky, I'll again just sort of give you a quick reminder. Okay? So if you just look at one of these digital things, let's just do a very simple thought experiment. Let's just count how many flip-flops we might have inside of this. Okay? And the reason I'm going to do this is because, if you recall, if I run something at 10 gigahertz and 1 volt, okay, all I need is 100 femtofarads to be dissipating 1 milliwatt. Okay? And by the way, I can build you a transmit analog equalizer that will do less than 1 milliwatt in terms of power. Okay? So how many flops do you get in 1 milliwatt at this 10 gigahertz? And by the way, that means, you know, it's 100 femtofarads. So how many flops do you get? Ballpark.
10.
Okay, yeah, I heard 10. Anyone more aggressive?
Any something like that.
Okay, yeah, I would say about 10 to 20 flops. Okay? How many flops do you think it's going to take you to build a 10-tap equalizer with 7 bits of resolution at the output?
1,000.
Okay, you said 1,000. I don't actually know if it's that big, but that's probably a reasonable estimate, right? Okay, so already you're burning probably 10x of the power in that digital equalizer than you are in the transmitter, you know, itself delivering the signal. Okay? So this is not to say that, you know, digital stuff is just bad and analog is beautiful. What I'm actually really trying to get at is that you have to be really careful when you do these things to really figure out what's actually costing you the power. Yeah?
I just have one quick question about this digital FIR filter. What happens if you actually do something like parallel, so every FIR actually runs slower than 10 gigahertz?
Right, so you can absolutely do, you know, so don't get me wrong, there is a very long list of optimizations you can do to try and make this FIR lower power, right? So you can try and parallelize the thing, you can try and, you know, do transpose, transverse, you know, transformations, you can do cut step retiming, you can do all kinds of really, you know, advanced stuff. And actually, if there's interest, I may talk about some of these sort of, let's say, digital FIR or general FIR filter design stuff at the end of the class. But having said that, you know, even if you do parallelism and stuff like that, okay, I'll let you run at the absolute minimum voltage, you know, for minimum energy per operation. I'll let you run at 300 millivolts, approximately. So you will save a factor of 10. And you may get close to the power of what you would have gotten with sort of some of these other types of tricks. Okay? So, and again, I don't want to push too hard on saying, you know, digital is bad and analog is good, but really what I'm trying to get to is that you can actually be pretty clever in terms of kind of trading off between these spaces. Okay? So I've shown you one solution that basically had kind of the largest possible parasitic capacitance at the output, but the simplest possible digital that you can come up with, right? The other extreme is this basically sort of FIR DAC kind of implementation, where the digital is the most complicated. And by the way, another optimization you can do is even build it as a lookup table, right, and not even bother to have flops. That's another very common thing. You know, so if you hear the term RAM DAC, that's what people are talking about. Okay? But you can see this. These are really sort of two of the extremes, right? Either I have a really complicated digital and quote-unquote minimum parasitic analog, or I have the most parasitics in my analog, but a very simple digital. Well, there's no reason why you actually have to do that. There's no reason why you actually have to be at one of those two extremes. Okay? It turns out you can actually trade off kind of in between the two in a kind of nice way. And the way you will do that is basically by sort of taking a look at what your channel actually behaves like, or rather what all of the different channels look like, and then just being a little bit clever in terms of how you partition between the digital and the analog. Okay? So just as an example, and maybe this is what you were sort of hinting at earlier on, imagine that you were to take one sort of segment like this. You say, okay, this segment has 0 to Imax over 2 of kind of tuning range. Okay? Then I'm going to have another segment over here, which also has 0 to Imax over 2. But for this segment, I'm going to allow it to choose either to take this digital data, which is kind of like, let's say, the cursor, quote unquote, this digital data, which is kind of delayed by 1, or this digital data, which is delayed by 2, right? Similarly, I can kind of play another trick over here. I can say, okay, well, this is, let's say, 0 to Imax over 4. And this one I'm only going to choose between D1 and D2, right? So you can imagine that I can still actually generate a pretty large number of different equalizers out of this. But in order to obviously pick how I came up with this, I'd have to really look at what are the channels that I could potentially be dealing with, and then make sure that for those sort of ranges of coefficients, I can always map the equalizer I would like to get into some structure like this. Okay? So this kind of general approach, not this specific design, this one is actually bogus, I just made it up. This general approach was basically sort of first talked about in a paper by Jared Zerby, a guy from Rambus. But again, really the point here is just that what you're doing is you're trading off between how much capacitance you've created at the output. You can see this particular design, I've sort of reduced it to about only an extra 0.25 of parasitic versus the original design. Which, of course, the more parasitic capacitance you have, the more sort of analog bandwidth you're going to be giving up, or the more power you have to spend to get that bandwidth. Versus kind of how complicated the digital over here ends up being. Right? Because you can imagine if I wanted to build some really complicated thing, I could put, you know, a mux here in front of each one of these little taps, and then, you know, I have however many of those different muxes, and then I have to sort of figure out all the control bits and things like that. So again, what I'm kind of getting at here is that there's always this kind of trade-off you can make between kind of the analog parasitics versus the digital complexity and power consumption. Okay? As you can imagine, the optimum really depends upon, of course, your technology and your data rate, right? Because if you're running at a speed where who the hell cares to put more parasitics here, fine, just do the analog thing, it'll be really cheap and simple. If you're running at a data rate where these parasitics just make it so that it's physically not even possible for you to get that data rate, okay, well, you should push more into the digital side so that you can actually make this thing work and be reasonably efficient, right? Does this make sense to everybody, or? Yeah.
So how much this DAXing can save you really depends on how different the channel is, right? So
That's right. So that's actually exactly correct. So if I told you were always operating over a exact given channel,
No, but okay.
then don't even bother with a DAC, right? Because I can build exactly the equalizer you want without any overhead at all in the analog domain.
Yeah, but I mean, it's like most channels are like low-pass channels. They won't be.
Mhm.
Oh, the pole will be different, but what I mean is like where the maximum post cursors are wouldn't be very different, right?
But here's the problem. Because the pole is different, it's going to force you to rescale things in a different way, right? So, for example, if I take, you know, a channel that looks relatively speaking like this versus another one that looks, let's say, relatively speaking like that, at the end when I rescale them, the heights are actually going to be different, right? So the range in the tap values also actually ends up being pretty different. And of course, I've assumed a really simple channel here, right? I could have, you know, all kinds of weird squigglies and overshoots and things like that, right? Okay, so so far we've been talking about kind of current mode kinds of stuff, because it turns out that that's really the easiest one to do, particularly in terms of doing these transmit FIR filters. But if you guys remember, we had this long discussion about voltage mode versus current mode drivers, and we said that voltage mode actually was pretty nice because it allowed you to sort of operate over a higher effective impedance. So just as a reminder, right, with a current mode, we're kind of talking about something that looks like this. And we said that for voltage mode, what you'd actually like to do is something that sort of looks more like this. All right, so this is, let's say, D, that's D bar, D, D bar, and this was 2RT, right? So this was like V out plus and V out minus, okay? So again, just as sort of a reminder, how much power was this dissipating sort of as a function of VDD the swing and the termination resistance. Does anybody sort of happen to remember that one? If not, I'll give you some hints, I guess.
4 times different.
What's that?
There's a difference of 4.
Okay, that's right. There was a difference of 4 between them. Okay, so maybe I'll just... This one is VDD times V swing divided by 2 over RT. Okay? The voltage mode driver is VDD times whatever swing you want to get times 1 over 2 RT. Okay? So factor of 4 difference, right? But now here's the question. How do you build an equalizer with something like this? So over here we said it's easy, right? I just take some of the current that used to be here, pull it over into another diff pair, right? And I just have more flops and things like that. How do I do it with this? Any thoughts? How do you get voltages that are not, and of course this thing over here is V swing. Actually, I should say 2 V swing to be precise. But so how do you get intermediate voltages?
Voltage regulator?
Oh, okay, so you said a voltage regulator. You're right, you could actually try and move this. But don't forget, I'm going to be doing that at 10, 20, 30, 40, etc. gigabits per second. So you are right, in theory you could do that, but that actually turns out to be really hard. Or not so straightforward, at least. What else can you do?
Switching the number of inverters? Or
Say that again?
switching the number of inverters?
Ah, okay, so when you say switching the number of inverters, what do you mean? You are right, but... No, you're right, keep going.
You have bank of PAs or I don't know. Whatever.
Okay, so you are right. You could do something where you took this thing and you cut it into a bunch of little pieces, and then you just chose sort of how many of those pieces you actually turned on at any one time. You could absolutely do that. Why is that actually perhaps not quite so nice?
Resistance changes?
There we go. The termination will change. Right? Now, it turns out that there's actually some people that have talked about doing exactly this design that you're talking about. What ends up happening is that the whole thing becomes nonlinear, because now your output termination varies with the data and varies with the equalization you're doing. And in fact, even that lookup table is nonlinear. Yeah?
Isn't that basically current mode? I mean...
Not exactly. It's okay, so the name that the people who did this called it is impedance mode, because what you're basically doing is you're just modulating the output impedance of your driver. Right? So whether or not it's current mode or voltage mode, this is where we get into the sort of, well, I don't know, because it's just a question of relative impedance. Right? So when you're doing a lot of swing out of the thing, it's probably a voltage mode. When you're doing not so much swing, it's probably a current mode. But it's just kind of modulating the impedance.
Yeah.
Okay, so that kind of works, but let's say that I forced you to keep the termination impedance fixed. Any other ideas? And by the way, while you guys are thinking about it, I'll switch over into my next set of slides, because that's where sort of I have space to actually draw it. So what do you guys think? Any other way to come up with sort of a voltage mode transmitter that can do equalization? And by the way, there's one solution in particular that's, let's say, quite straightforward. If I give you a fixed input voltage and I want a variable output voltage, let's say in a DAC or something like that, what's like the dumbest DAC you can do? Any thoughts?
Resistor divider.
Yeah, resistive divider, right? Okay, so the way you would do this in this particular context looks something like the following. And by the way, I'm just going to draw one side now, so keep in mind it is differential, but I'm just going to draw one side because I want to make my life easy. Okay? So I can basically have my main data here, delay it by, as an example, 1 symbol, feed it into another one of these guys over here, and then just short their outputs together. Okay, and let me actually draw this a little bit over there because I'm going to mark on this thing in 1 second. Okay, so this would be like my V out, for example, on the plus side. So, just as a reminder, you might have like that 2RT going to the other side. Okay? So indeed, this basically works, because if you sort of think about it, let's just say that I kind of partition the widths here. Right? So as an example, if I used to have some W total to get a certain impedance, if I now just sort of split that W total between the main driver and this, let's say, equalization driver, then when I look back into here, I kind of have the same total transistor width driving it, right? So I'm kind of saying that W total is fixed. So what that means is that also my termination impedance is fixed, right? Because that basically means the total conductance on that node is fixed, okay? But the way you generate an intermediate voltage is basically, as an example, let's say that this data was, different from that data. Then that would mean that, for example, this NMOS over here would be on, and this PMOS over here would be on, right? So then you'd basically have a resistive divider that would create some intermediate voltage, okay? And by the way, this particular design was done by a guy named Jackie Wong. This is from JSC 2004. So indeed, this works. You can imagine you can keep on partitioning this more and more, right? You could have more taps. You could have more control over the taps by just sort of changing this relative width. Indeed, it works. But turns out actually has some fairly significant drawbacks. So what's the drawback for this, for doing things this way? Why is it bad to generate this intermediate voltage in this particular way that I've drawn here?
Big power?
What about the static power?
So,
You're right, there is some static power issue, but go ahead.
Yeah, so current will basically flow from PMOS into NMOS, and it's like a DC power.
Okay, that's right. So what you're going to have happen is there's going to be conditions where current is going to flow straight from that PMOS through that NMOS. Now remember, even in the original driver, I also had static power because, right, I always have one thing pulling up and one thing pulling down. But let's actually, be very, let's say, specific. Let's say that I made it so that this had half of the width and this had the other half of the width. What would be my output voltage, differentially speaking, under this particular condition where the PMOS is fighting with the NMOS?
0.
Yeah, it'd be 0, right? How much current would I have? And by the way, remember, I'm trying to keep the termination correct here. How much current would I have?
VDD over 2RT?
Yeah, I have VDD over 2RT on this side. And by the way, on the differential side, I also have VDD over 2RT. Okay? So kind of the nicest way to sort of think about what the problem here is, and in case you guys didn't get it, the issue here is that what happens is that because we're sort of shunting this current to ground in order to reduce the output signal, we're actually going to be burning more current to send less signal, right? So for those of you guys who are, let's say, thinking PA speak, this is like, the exact opposite of what you'd like to have happen from an efficiency standpoint, right? Because, you have more current with less output signal, right? Okay, so the cleanest way, or the way I kind of like to think about this is, if you do a plot of power divided by this VDD times V swing divided by RT, which is kind of like the normalization thing that's the same for everybody, and then you look at what that power is versus the transmitted sort of output actual analog voltage. So with the current, with the current mode design, basically it doesn't really matter what output voltage you're generating. It's always the same amount of power, right? Because basically you're just steering current back and forth, so however much current you're using is always the same. Okay, so that's like the current mode design. Okay? If you do something like, and by the way, I'll just label this point right here is 2. Okay? Well, remember we said that with the voltage mode design, if I always transmit these 2 points, then I always get this 1/2 factor. In other words, I get 4 times better than the current mode design, right? But remember, we just said that if I transmit 0 output voltage, I would have effectively VDD over 2RT on the positive side and another VDD over 2RT on the negative side. In other words, the total current would just be VDD over RT, right? Which means, basically, that's going to sit at 1. And so if I put a 0 here, I have another dot like this, okay? And if you actually look at sort of, how you would do something like this, what you'll see is that the current versus the output voltage does something like this. Okay, or rather the power versus the output voltage. In other words, as we said before, if you transmit less signal, you'll actually burn more power. Okay? Now, notice this is still always better than the current mode design, but you've lost a factor of 2 in the worst case in terms of your sort of net benefit in efficiency. Okay? even more than that, and this is sort of something that you could debate about whether you need to sort of worry about it. Now what is going to happen is the amount of current you're dissipating is going to change with the data pattern. Okay? And remember, sort of supply noise and things like that could be pretty big compared to your signals you're dealing with. So having the current in that transmitter change is also kind of not necessarily the best thing to have happen. Okay? So that's kind of the bad news. The good news is there are actually ways of fixing this. Okay? And the simplest way of fixing this, or at least I should say conceptually, one of the simplest ways of fixing it is basically instead of allowing the current to flow directly from sort of one side of the transmitter to the other, what you will instead basically do is introduce some extra devices that kind of act like bridge switches in between. Okay, so let me just draw kind of what this looks like. These are intended to be kind of a segmented driver, meaning there's a lot of different segments that you can turn on and off. Okay, so what we're basically going to do is something like the following. And now this is like, let's say, the positive side. So that's, let's say, V+. And then we basically do sort of the same thing on the other side. This is going to be the V-. Okay? So the idea here is pretty simple, right? So you can imagine that basically, if instead of, for example, having one of these connected to either VDD or ground, if you want to get less output signal, what you'll instead do is turn on one of these bridge switches. Okay? And the trick here is just that by turning on the bridge switch instead of one of these devices, you're still going to force all of the current to flow through some extra series resistance. Okay? So in other words, when you get less output, you're actually doing it by sort of introducing just a path for current to not flow to the output. Okay? But you're not actually taking extra current in order to do it. Okay? So for this particular design, if you sort of repeat that same plot we had a second ago, where again this is just power normalized by VDD V-swing over RT. And this is again sort of the analog voltage. So that's minus V-swing. This is plus V-swing. Right, so we said current mode was up over here at 2. We said that, standard voltage mode with kind of the equalization structure we drew on the other page did something like that. Well, if you do things right for this particular design, and by the way, this was presented at ISC last year, if you do things sort of in a particular way, then you can actually make it so that the current is constant independent of what you're really transmitting. Okay? So this indeed sort of works. And gets rid of that sort of current variation problem. It also keeps the sort of, let's say, the constant output current, which again can be a nice benefit. But there's again actually some problems with doing this. So any thoughts as to what the, let's say, annoyances with doing this particular design might be? I'll give you guys a hint. I didn't draw sort of all of the control stuff on this thing for a reason. So what's the problem with this particular design? How do you sort of guarantee that the current is constant, but the impedance is also constant as you change the output voltage?
You have to modulate the resistance of that middle pair, or?
Basically, yeah. So what ends up happening is that if you really want to get this particular curve here, there's a rather nonlinear equation that you end up with in terms of what the value of this resistance should be and what the value of that resistance should be as a function of any particular transmit swing setting. Okay? So it's not that that can't be done. It's just that when you end up with something like that, you have to build a whole bunch of crap in front of this thing just to sort of get it to behave the way you want it to. So usually people do it with some sort of lookup table or something like that. But remember we said that, the whole reason of doing these kind of transmitters in the first place was to try and keep the power small. Well, if I have a big lookup table to kind of correct all kinds of weird things or sort of do some weird nonlinear mapping that I don't want to deal with, tends to make it harder to actually really get this thing to be as efficient as you'd like. Okay, so this particular design actually I believe was going up to about 7 gigabits per second or so, and was dissipating about 34 milliwatts. Okay, and so again, just to give you some numbers, if you sort of compare that to what you would get from even, let's say, a 500 millivolt sort of peak-to-peak differential swing kind of thing, that's probably about a factor of 5 or so extra power. Okay? So again, not that this is a bad idea, just you have to be really careful with, when you do something to try and fix a particular problem, watch out for what happens in the sort of drivers in front of it. Because very easily you can actually spend more power on those drivers that are fixing the problem than you would have spent to just deal with the problem in the first place. Okay? Does this kind of make sense to people, or? Yes, no?
500 millivolts thing that you were talking about, what number was that again?
Oh, so I was just saying if I did a driver that was capable of 500 millivolt differential peak-to-peak swing, right, and let's say it was running off of a 1 volt supply, then we can quickly calculate that. Let's say that, we said that this V-swing was a half a volt. We said the VDD was, let's say, a volt, so that's 0.5. 0.5 over that RT is 50, so it's 0.5 over 50. So that's about like 10 milliamps or something like that.
Zero flexibility.
Oh, actually, sorry, it's not even 10. It's actually 5 because I forgot the factor of a half.
But that didn't have any flexibility, whereas this one had
Fair, but you just paid a factor of 7 for that flexibility. So I agree. No argument. But nonetheless, the question is it worth it? Right?
This particular one had like a lot of different...
Yeah, no, don't get me wrong. Again, I'm not saying this is a bad idea. I'm only saying that anytime you come up with one of these ideas, you have to be really careful to think really sort of, or I should say, you should think really carefully about what the implication on everything in front of you actually is. Right? Because, again, if I'm only talking about a few milliamps, and then I introduce all this other stuff that costs me 10 milliamps, then, it's a question as to whether it was worth it in the first place. Right? That's all. I'm not trying to bash this particular design. I think this is actually a pretty interesting design. I'm only saying there's this general issue of overhead really matters, right? Because even though there's all, we like to talk about the analog and mixed signal and high-speed stuff, all of that, flops and XOR gates and etc. ain't free. That's kind of the point. Okay? Make sense to people, or? Okay, so now that we've kind of beaten transmitters to death, I did actually want to talk a little bit about how you might do receive FIR equalizers. Okay, so we'll talk about DFEs as well. But I want to just briefly talk about some of the receive FIR designs also. Okay, so as I've kind of mentioned a couple times already, these things, at least currently, are not very popular. Okay, so to maybe sort of answer why that is, let's just sort of go through and draw how you might actually build one of these things, at least in the most straightforward way. Okay?
By this, you don't mean DFE?
I do not mean DFE. I mean a receive linear equalizer that's an FIR. Okay, so in other words, I don't mean the continuous time linear equalizer. I mean an actual sampled data receive linear equalizer. So I'll draw what it looks like, and maybe it'll be more obvious. So I take my analog input voltage, okay, and then what I basically do is, to get my sort of sample delays, I'm going to need some sort of sample and hold, right? So these are just literally implementing the sort of Z inverse. And then what I do to actually create the sort of coefficient weighting is, just as an example, I can build some transconductance cell, right, that's hanging off of each one of these little taps here. And then again, just like I did with the transmitter, just add them all up. Right, just current sum them at the output node. Okay? Is this more clear as to which equalizer I'm talking about now? Okay. And by the way, I drew this again as being single-ended. Same thing works differentially. Okay? Or rather, you usually would actually build this differentially. So now, why is this not so popular? Why is this kind of not so much fun to do in comparison to the transmitter? What do you guys think?
Analog sample and hold is different.
Okay, so I've got these analog sample and holds. So, just as an example, what might actually be inside of that box? How might that look in the most straightforward case? Okay, we'll do that one version in a second, but even without the op-amp, what's like the dumbest sample and hold you could do?
Transistor and cap.
Yeah, I could just have basically, and by the way, you turned out to need 2 switches because you want the equivalent of a flip-flop. You'd do something like this, right? You'd, let's say, do clock bar and clock, right? Okay, so now you already said that you need an op-amp or something like that. Let's see if we can figure out why that is. So what's wrong with this particular sample and hold? I mean, there's actually a long list of issues, I suppose, but let's just pick off a couple of them. Why is that one annoying or bad?
Output impedance.
Say that again?
Output impedance.
Okay, it has a high output impedance, right? That's certainly true. What else is bad? Okay, you said, yeah, it leaks. Okay, that's also true. Anything else?
Charge injection.
Okay, there is indeed charge injection, so you guys are all complaining. Oh, okay, so the output impedance is fundamental. What was it you said again? Oh, leakage. Okay, that is fundamental. I'll even give you a perfect switch. You said charge injection. That's also true. I'm still going to give you a perfect switch. There's still something wrong.
You need to drive it somehow.
Okay, yeah, I mean, let's assume there's some buffer over here.
All right, but the ones in between are sort of charged off the other ones.
So what exactly? So why is that bad? What happens, when I just charge this guy up and then connect it to the next guy over here? Why is that bad?
Charge redistribution.
Yeah, basically what happens is there's only a certain amount of charge you dumped on that cap, right? So then when you connect it to the next cap over here, guess what? You just get charge sharing and you have less voltage than you used to have, right? So immediately you just have loss in your sampler, right? Okay, so now because of that, you tend to need some sort of, it's not necessarily really an op-amp, but you need some sort of buffering. And depending upon, let's say, how aggressive you want to be, that buffering can look anything like actually needing, 2 buffers in each and every single one of those things. Okay? So now this really looks kind of like a flip-flop, right? Just obviously in the analog domain. Okay, so really the story about why this is bad news is that essentially all of the sample and hold offsets, so that's like the charge injection kind of stuff, all of the noise, and all of the just general errors you get from those samplers, unfortunately, accumulate. Right? So if I was going to have a chain of like 10 or 20 of these things, by the end of the chain, you're going to have all kinds of noise and junk like that accumulating. Okay? So that's actually the main reason that people tend to not like using these things. Now, it's not to say you can't possibly build one. It's just that if you want to build one that doesn't have these issues, you're just going to have to spend power to fix it. Right? So especially if it's something like noise, you have to up the sampling caps, you have to up the GMs on your buffers, and so on and so forth. Okay? So that's actually basically really the main reason that people are not such a big fan of these things. There's actually one other thing which is maybe not so bad, but is also a little bit more annoying in terms of how you build these. So how would you build this transconductance cell here? Let's try the simplest, dumbest thing first. What's that going to look like? Not a trick question, by the way.
Diff pair?
Yeah, just diff pair, right? Okay, so let's build this as a diff pair. Okay, now, how are you going to tune the gain of each one of those coefficients?
Current source.
Okay, what about the current source?
Tweak the.
Okay, let's indeed tweak the value of that current source. So this indeed works. Or I should say it sort of works. Why is this bad? Like, what's the really annoying thing about this?
Output column mode.
Okay, the output column mode will change as you change the gain coefficient. There's actually something even more annoying.
Everything changes.
Everything changes, right? The linearity changes, the gain changes in a nonlinear way, the output column mode changes. Basically, you can indeed do it, but it's kind of really hard to guarantee that things are operating where you still wanted them to be in the first place, right? Because you can imagine if this thing used to have, let's say, in the peak it has a milliamp, and then you drop it to 10 microamps of current. And by the way, you might indeed need that kind of dynamic range on the equalizer coefficients. Guess what? The thing ain't going to operate at all linearly when you dump the current to 10 microamps, right? Because it's going to be way in subthreshold. It'll clip things, and you won't really get the filter that you actually liked. Okay? There are some things you can do to kind of fix that, but again, for these kinds of reasons, people typically don't like dealing with it quite so much. Now, as much as I've sort of complained about receive linear equalizers, it turns out there are actually some tricks you can play that will let you at least mitigate some of these problems. And in particular, you can actually mitigate some of these problems with a sample and hold. Okay? So one particularly sort of, I wouldn't say necessarily popular, but particularly interesting way of mitigating some of these issues with a sample and hold is basically to do this thing that's called coefficient shuffling. Okay? Now, by the way, the idea with kind of the couple things that I'm going to be showing you here is that it turns out you don't necessarily have to cascade sample and holds. You can actually do them sort of all in parallel. but still get the filter functionality that you'd like to have. Okay? So the idea for how you do, let's say, one version of this is kind of shown here, and this is actually a paper by Lee and Razavi from CICC 2001. Okay? So here's kind of the trick. So let's say that I have this sort of parallel bank of sample and holds here. Okay? So let's say, sort of, in this particular case, I'm doing a 3-tap filter. Okay? So let's say that in, let's say, the equivalent of, quote-unquote, the first time slot, what I'm going to do is kind of, let's say, the most straightforward thing. Right? So I basically say, okay, the main cursor data goes through this coefficient C0. The data that was 1 before goes through this coefficient C1. The data that's 2 before goes through this coefficient C2. And I just add them all up. Okay? Well, what I can do now is on the next time slot, remember, what I don't want to do is cascade the sample and holds. But instead, if on this next time slot, what I actually do is I just basically resample everything again, but just shifted in the way I do the sample. Then what I could do is I could take this thing that, for example, what used to be in the sort of first time slot, but now I've just done it one sample later. Now I'm actually going to take that and feed it to this coefficient C0, right? This other sample over here, which if you sort of think about it, and maybe I'll just draw the clocks here so that it's, maybe a little bit more obvious. Actually, I'll do it down over here on the right. So I would have these sort of 3 clocks like this. Oops, phi2. And of course this repeats. Okay? Now in kind of this next time slot, meaning, for example, when this phi1 is on, what I will basically do is, again, I'll take the sample that was from this intermediate point, feed it to this coefficient C0, take the sample that was from here, actually from here, because that's going to be sort of 1 later, right? Feed it over here, and then take the sample from there, which is now 2 later, and feed it over here. Okay? So again, I can actually do sort of the same thing in the third time slot, but just again, by shuffling which coefficient, I apply to which one of these sampled pieces of data. Okay? So again, the advantage of doing this is that now I just have one, like I never go through multiple sample and holds in series. Right? I just have a parallel bank of sample and holds, and then all I'm really doing is shuffling which coefficient I apply to which one of those sample and holds. Okay? So I think it's actually useful to sort of look at how you really do this, because it doesn't really make sense usually until you do that. But just to sort of give you an idea, you can do this either by shuffling the digital coefficients, meaning you'd always have the same sample and hold and the same analog amplifier afterwards, but you just sort of change the digital DAC codes. Or you can equivalently sort of shuffle the analog inputs around. Okay, so I'm going to draw the version where you shuffle the analog inputs, but the digital shuffling is basically just as valid. Okay? So this thing will look something like the following. So if this is my analog input, at the front end, again, I'm just going to sample it with 3 parallel sample and holds. Okay, so that's phi0, that's phi1, that's phi2. Okay? And then at the output over here, again, I'm just going to have 3 sort of GM stages, but now with these fixed coefficients for my different taps. Okay, so let's say A0, A1, and A2. Okay, and as usual, I'm just going to sum these together at the output. Okay, so this is going to be my Vout. And again, I'm drawing this, in the so-called single-ended version, but differential is obviously works the same way. Okay. So now what I'm going to do is I'm basically just going to distribute these 3 samples to kind of each of these things, but just depending upon which time I'm in, I'll decide which one I'm actually distributing where. Okay? So let me just go ahead and draw it, and then hopefully it'll be sort of more clear as to how something like this would work. Okay? So that's that. That's this. And that's this. And then finally, of course, I'll have this one as well. Okay, so now what I'm going to do is I'm just going to fill in what are the clock phases on those different switches, so that hopefully it'll be sort of more clear as to what's going on. Okay? So remember, what I'm trying to do is that, let's say on this first clock phase, which is just when phi0 will be high, what I'm trying to do is I want to take whatever, let's say, my current piece of data is, and that should go to A0, right? Okay, so as an example, that would mean that this switch here would be controlled by, and I'll just draw it a little bit smaller to be consistent, that switch there, when it's phi 0, that switch would be on. Okay, in other words, I'm feeding the first sample into that A0 coefficient, right? Okay, then similarly, over here, oh, oops, sorry. Did I do that right? Yeah. Actually, is that right? No, that's right. Okay, so this would be here, okay? Because that's just 1 before, right? So that's what I would look at that point. Oh, actually, let me, well, no, okay, there we go. Okay, so, oops, that's not what I wanted. There we go. Okay, so all I was trying to do there was basically, again, when it's phi 0, I want my main tap to go to my A0. I want 1 before to go to my A1. And I want 2 before to go to my A2. Okay, so that's going to mean that this is actually going to be down here like this. Okay? So now, basically the idea is that we're just going to be shuffling these things around, right? So as an example, now when my phi 1 is actually on, again, I want my 1 sample to go to the A0 coefficient, right? So basically that would mean that on this switch right here, I will choose input 1 when clock 1 is high, right? Okay. Similarly, down over here, when clock 1 is high, what I want is for the thing 1 later from it to go into A1, right? Well, 1 later from phi 1 is phi 2, okay? So that's why I select this one right here. And then finally down here on the bottom, the thing that should be 2 later should be selected into A2. 2 later, just because these things all wrap, right? They're repetitive. Right, 2 later, 1 later would be here, 2 later is there. Okay, so that's why you select this over there. So finally, just to complete it, as you can probably imagine, all of these are 2. Okay, so what you can kind of see is happening is just that as you walk from there to there, right, I start with a 0 on the top here, the 0 moves down by 1, 0 moves down by 1. Same thing for all of the other ones, right? The 1 starts here, moves down by 1, moves down by 1 more, which means that it gets flipped up to the top. Does this kind of make sense to people, or? Okay, great. So we're out of time for today. So again, no lectures next week, so we'll pick back up the following week. So see you guys then, and have fun at ISC.